Hey guys, hopefully you had a chance to watch the last two videos. The first video talked about stream function, Laplace equation, and potential function. Second video talked about elementary flows, especially uniform source sink and doublet. So in this video, we're going to talk about the vortex flows, the other remaining elementary flows, and we're going to see how we can use that vortex flow to uh, kind of simulate Magnus effect. And from there, for the first time, will we we will figure out a way to actually find predict lift theoretically. Now, again, for the first time in the history of aerodynamics, that people were able to do this using these just rudimentary concepts that Lagrange and Laplace developed, right? So, all right, let's get to it. So in the last video, we talked about how we can combine uniform and doublet flow to create a flow over a cylinder. We have the stream function for uniform flow, stream function for doublet flow. You put them together and you can find the stream function. And if you plot the stream function, you get, the streamlines that you will get the flow field, which looks like streamlines around a cylinder. We also talked about how we can find the stagnation point because without knowing the stagnation point, where the stagnation point occurs, you cannot find the surface you cannot find the surface that can be covered with just you can replace the surface streamline with a solid object, and that sort of resembles flow going over that solid object, right? So, but today, now we will also talk about how we can actually find surface velocity and pressure. Say you were able to determine the stagnation points, and you were able to find the streamline that is going through the stagnation point, and you say that, okay, that will be my surface of the object. Now we got to figure out how we can actually get the velocity and pressure distributions around the object, right? Well, you may know that the first thing to start, if you want the velocity and pressure around the cylinder, um, first you need the surface of the cylinder, right? So you need the x and y locations of the cylinder. So how can you get the x and y location of the cylinder? Well, that's pretty straightforward, right? Using polar coordinates, we can get x equals r cos theta, y equals r sine theta. And now you guys know that r is the radius of the cylinder, which is a function of the doublet strength, right? So as you increase the doublet strength, your size of the radius of the cylinder will go up, right? Now you probably can guess how you can find the surface velocity and pressure, right? Well, so these are the coordinates of the cylinder, right? You change from 0 to 360, and you basically plug this in u and v equation, and you will actually get the velocity distribution, so the velocity component around the surface of the cylinder. And once you know the velocity, then you can really, you can find the pressure using Bernoulli's principle, right? So it's pretty neat. All right, so as you can see, the flow over the cylinder kind of resembles, a kind of like Stokes flow, where the flow going over the object, it starts at a stagnation point, and then the flow goes around it, and then there's a stagnation point in the back, and then goes straight. So if you take, if you consider the symmetry of the flow about a certain axis, we can see that the flow is identical or symmetric about the y-axis, and flow is symmetric about the x-axis. So the flow is symmetric and the velocity is symmetric. If the velocity is symmetric, the pressure is symmetric. So all this says is that, this shows that the cylinder has no drag, which is sort of not what you expect, right? I mean, any object moving in a flow has drag. Back in the day, people actually called resistance. So before Prandtl, the concept of flow separation and drag and friction was not well understood, right? They were, back in the day, people were just dealing with or trying to take the baby steps to simulate flow over an object with the assumption that the viscosity doesn't play big of a role, right? But that's why this paradox that exists, that when you simulate flow over a cylinder using a Laplace equation or Euler's equation, you get something which resembles something like this, which allowed the researchers, the mathematician, to see like, hey, why this behaves like there's no drag? Well, it's obvious because, they didn't take the friction and viscosity into account, which again was not even thought of before Prandtl, right? So that led to D'Albert's kind of made this paradox that it seems to me that the theory or potential flow developed in all possible rigor gives, at least in several cases, a strictly vanishing resistance, a singular paradox which I leave the future geometeers to elucidate. Right? He didn't leave it to engineers. He left it to mathematicians to figure this out, which is which makes sense because mathematicians. It basically took all the mathematicians, all the good mathematicians, to actually predict or develop the theories which will allow us to simulate flow over an object, right? So that sort of tells you how important math is to this field of aerodynamics. So it's practically built on fundamental math. Right? So you may wonder, so how does a flow around a cylinder actually look like? So, flow around a cylinder is a classical case. People study this a lot because it has some very, very interesting features when you expose the cylinder to different Reynolds numbers. So, here are the three different flow fields that a cylinder in a flow can experience. So one, classical, there's no separation right there, right? And then you have a separator steady flow where you have these two recirculation regions behind the cylinder. In some cases, you also have this oscillatory flow, or what we call the von Karman vortex streak, where you have the alternate shedding of vortices that is formed around, that behind the cylinder. And you also have what is called a laminar separated flow field, and then a supercritical case where the flow field transitions to turbulence, and you have a really narrow wake when compared to the other cases. So you have these different types of flow fields that exist on just one given object, right? So it kind of makes you wonder why this is happening, and what we can do to understand this much better. So before we talk about that, here are some of the interesting von Karman vortex streak that appears in nature. There is we can see the vortex shedding of an island over here. So again, I believe these were taken by the International Space Station crew. So here you have some of the islands, and you can see the vortex shedding behind those islands, and you can also see the cloud right here. Which is pretty cool, right? I mean, you will see these pattern of vortex shedding a lot because it so happens that the Reynolds number at which this vortex shedding occurs is more common. So here is how this coefficient of drag varies with the Reynolds number. Now, if we were to do this in class, I would pause here and ask you guys to look at this graph and sort of like understand what's going on, right? Let's do the same here, right? So pause this video right here and look at this graph and understand what's going on for the CD with function of Reynolds number, and then mostly think about why this is happening, right? What causes this drag variation to decrease this way, right? So think about it. All right, so now I hope you had a chance to think about why this actually behaves this way. Why is the CD variation with Reynolds number has this very interesting curve, which is typical for a cylinder, right? So let's look at the flow field at these different cases. So I really hope you thought about what you think happens at this point right here, right? So we sort of talked about this, I hinted on that in the last slide. But let's look at the flow field, right? For a smooth sphere, let's just look at the smooth sphere, not a rough one. So for a smooth sphere, at about point B right here, you kind of form what is called these, laminar separation bubbles or recirculation regions behind the cylinder. Even though you have the wake, that's practically steady, right? So as you move from, you can probably imagine what you think happens at A. So at A, we have the Stokes flow where the flow over a cylinder, the Reynolds number is really, really low, which means it's a viscous dominated flow. So the drag coefficient is really high. Even though the flow may look symmetric, what happens is that it causes a lot of friction. So the wake you know, just because there's no wake doesn't necessarily mean there's no drag. Imagine you drop a cylinder in honey, right? So, and then you really have to push on it for the cylinder to actually go, through the honey or a really high viscous fluid, right? So otherwise it'll just, may sit there. So that kind of shows you that even though flow that is going around the cylinder or an object may look symmetric, the viscous forces still play, and the drag coefficient is a lot higher, right? So as you increase the Reynolds number, you have these, again, laminar separation regions or circulation regions that is forming in the back on the wake of a cylinder. The reason why we call this as like a laminar separation bubble or a steady separation bubble is because, even in the wake, you take a single point right here and then you measure the velocity as a function of time. For the most part, it stays constant. So that's the definition of laminar flow, right? So, but as the flow transition from the Stokes flow to this type of flow, your drag coefficient goes down. And then something interesting happens when you increase the Reynolds number even further. So around this region, you have this one carbon vortex street. As you can see, when this happens, the drag coefficient stays, almost constant, anywhere, somewhere between like 1 and 2 right here, right? And as you keep increasing the Reynolds number, at some point, the one carbon vortex street is going to stop, and you have just pure separation, and this flow separation happens right around this top layer, top and bottom portion. So you'll get a fairly thicker wake, which also increases this drag coefficient just a little bit, as you can see. Then it dips down and then rises up again. So now, if you keep increasing the Reynolds number, what's going to happen is that the separation point is going to get pushed towards the back of the cylinder, which decreases the thickness of the wake, which decreases the momentum deficit, and that basically will reduce your drag, right? Which is pretty cool, and this is basically called the supercritical station or supercritical Reynolds number, where the transition from laminar to turbulent happens much later in the surface of the cylinder. Right? I hope you found this interesting. So if we talked about CP variation in class, right? So I'll let you look at the CP variation and actually try to understand what's going on as a function of the the theta, which is basically the surface of the cylinder, right? So pause here for a second. Look at the CP variation for the smooth, subcritical, and supercritical Reynolds numbers, and try to understand what is really going on, and see if we can relate the CP distribution to what's happening in the flow, right? I'll leave that as an exercise for you guys to do. Okay. All right. So, you may ask, you may wonder why there is dimples, why there are dimples in golf balls. So, what really happens here is that, as you can see, for a smooth sphere, the separation happens much early on, but for a golf ball with dimples, the separation is forced to move much later in the surface. So the separation happens in the back of the cylinder, right? So, or back of the sphere. So it happens right here, which reduces the thickness of the wake, and which again reduces the drag coefficient. So here is a drag coefficient variation for a smooth sphere and a golf ball. It looks like you see much drastic reduction in drag coefficient as a function of Reynolds number, which is again pretty cool, right? All you do is you force the boundary layer to become turbulent, and then because turbulent boundary layer really has a little bit of high energy when compared to laminar boundary layer, so it stays attached much longer. It works the same way as vortex generators on airplanes do. So I'm not sure you have looked at it before. So there are tiny tabs that pops up on the surface of the wing, right? So they create these vortices which energize the boundary layer, which you really use to keep the flow attached at much longer times. And the benefit of doing that on a wing is that you can stay attached at the flow can stay attached at a really, really, really high angle of attack. So That means that you can you can take off and land very at a much shorter distance, right? But the downside to that is on an airplane, for a wing where skin friction is dominated, it increases the drag, skin friction drag a little bit. But on a on a on a sphere or a cylinder, which is a bluff body where the pressure drag dominates and skin friction drag doesn't really play much big of a role. So the reduction in pressure drag is much greater than the increase in skin friction drag. So the overall drag basically goes down. Okay, a lot of people have done a lot of studies on, what type of what the shape of the dimple should be. I'm sure you have seen golf ball with like pentagon type dimples, hexagon type dimples. There are a lot of studies on how much depth the dimple should have. So a lot of CFD and also like experimental studies that are out there. So if you go to just Google Scholar and type golf ball or dimples on golf ball, you'll find a lot of resources. And also people have tried doing that on a wing, just to see how dimples on a wing will affect. At some point, at some cases, some Reynolds number, it works, it has benefits, but then again, as I mentioned, the dimples on a wing and golf ball works much different because a wing is a streamlined object where skin friction is dominated. So even though it helps make the flow attach a little longer, really increases the skin friction drag, and the net benefit is not as high as you would expect when compared to dimples on a golf ball. So that's one of the reasons why you don't see dimples on airplanes or dimples on airfoils or wings. All right, moving on to our last elementary flow, which is the vortex flow. Vortex flow, as you can see, is represented in this image. So you have flows which is going in concentric circles. Okay. Now let's think about velocity components of this. You probably can guess, it's sort of opposite to what we saw in source and sink flow, right? Again, there's no tangential. Well, the tangential velocity along a streamline is a constant, and there are no radial velocity, and the velocity varies inversely with distance from the center. So let me put this in an equation format. So which to say that v theta, again, Vr is pretty much 0, right? So you're just left with v theta, which varies inversely with the radius. So that means as you move farther from the center, right? As you move farther from the center, your velocity or v theta goes down. Okay, and c is just a constant, right? Now let's take the circulation again. We talked about circulation, right? Which is just a line integral of velocity around a given loop. So we can take, say, for example, the streamline and basically integrate the velocity in here along a circle. So basically, v theta, you integrate that from 0 to 2 pi r, okay, it's perimeter, right? And you get v theta times 2 pi r. So rearranging that, you can actually find that v theta is nothing but gamma by 2 pi r, and gamma here is the circulation, right? So it's a circulation which represents the strength of the vortex, right? So again, you are familiar with circulation. You guys calculated vorticity in circulation for an experimental data for wingtip vortex and the leading edge vortex. So you should be familiar with this concept of circulation by now. So as you can see, it varies inversely with the radius. All right. So in polar coordinates, again, we know that Vr is 1 by r, dou psi by dou theta, v theta is minus dou psi by dou r. So all we're trying to do here is basically get a stream function for this vortex flow, right? So again, I really hope you're still having the handout next to you when you see these videos. So make sure that you solve this equation by yourself first before you watch this video, so that you guys can understand and follow along what's going on. Okay, so ultimately, when you find the stream function for a vortex flow, it's going to be minus gamma divided by 2 pi logarithm of r, or natural log of r. So here, it's in polar coordinates. Now let's convert that to Cartesian coordinates, and you basically get ln of r is square root of x squared plus y squared. right? So, which is again, hey, you can represent, you can draw a vortex flow field in a flow, you can simulate that in your computer, which is pretty cool. But there's a slight change that I wanted to note here on the vortex flow, because the radius of the vortex, or the radius of the cylinder, in the last elementary flows, when we combine uniform and doublet flow, if you remember, the radius of the cylinder is basically controlled by the strength of the doublet, which is the kappa, right? So we really need some way to make sure that when we superimpose the vortex flow onto a cylinder, that the surface streamline becomes constant, or it has the same value as what you observe when you superimpose free stream plus doublet, right? Let me show you what that means then. So for a stream function, and determine with a you can determine with an arbitrary constant, right? So you just add, because stream function, all stream function is a constant. So if you remember the first time when we introduced stream function, it just on the right hand side you have the function, but that's equals pretty much a constant. So it won't be far of a stretch to actually add another constant to the stream function equation, right? So again, I'm just gonna call that constant as gamma by 2 pi ln of r, and this r is the radius of the cylinder, okay? So, and we know that r is controlled by square root of minus kappa by 2 pi infinity, and again, make sure the kappa is a negative, right? So when you substitute this in here, you basically get this equation, right? Logarithm gamma by 2 pi ln small r plus gamma by 2 pi logarithm of capital R equals that, just basically the ratio of the radiuses. So in the end, you basically get this term. Now think about it. What happens when this radius, the small r, equals capital R, right? When that happens, this ratio goes to 1. So that means logarithm of r goes to 0. So you get stream function of 0 along the radius of the cylinder, which is pretty cool because that's exactly what you should get when you superimpose free stream plus doublet flow, right? So that's why we normalize this. I hope really you understand why we do this step, right? So once you have that, once you have this equation, and again, you probably can guess what x naught and y naught represents, right? This is the location at which you pose, you kind of put the vortex flow in the Cartesian space, okay? All right. So again, if you want the flow field, just program the stream function equation, just differentiate with respect to u and v, you get, with respect to x and y, you get u and v velocities, which is pretty cool. Now comes the fun part where we actually combine uniform flow plus doublet flow plus vortex flow, right? When we combine all that, you probably can guess what you probably can understand or sort of like predict what you would expect to see, right? Yes, you actually get a flow over a rotating cylinder, right? Because uniform plus doublet flow gives you the cylinder, flow over a cylinder. Adding vortex flow adds the element of asymmetry in the flow field. Because, remember how we talked about, you can think of, combination of a vortex and the free stream as a phenomenon that produces lift, right? The same concept we discussed when we talked about bound vortex, right? So if you superimpose free stream onto a vortex flow, so again, in a vortex flow, the streamlines are going in a given direction, say clockwise. So when you superimpose free stream in here, due to, again, the additive property of vectors, right? The velocity vector on top is going to be much greater when compared to velocity vector on the bottom. So you get a velocity gradient. So if there are changes in velocity, and if that is acting on a certain object, you can actually determine the pressures, and from there you can determine the lift, right? Which is pretty cool. So, instead of, we will get to how we can use this to simulate flow over airfoils, but now you can simulate flow over rotating cylinders, and the rotation is controlled by the strength of the vortex, which is the circulation, right? Look at that, it's pretty cool. And watch what happens to the distance between the streamlines. Again, distance between the streamlines indicate velocity, right? Velocity vectors, right? So as the distance between the streamline reduces, your velocity goes up. That's exactly what's happening, right? And you can use the same concept of determining the stagnation points to determine the surface of the cylinder, and also you can predict what the velocity variation around the cylinder look like. And from the velocity variation, you can determine the pressure, and from pressure, you can actually get lift. But or you can do all of that, or if you want to get lift, you can just use the Kutaji-Kasky theorem, right? Lift equals rho v gamma, right? And you will actually get the net lift that is acting on a cylinder. What's so beautiful about this is that for the first time in the history of aerodynamics, people were able to simulate flow over a rotating flow field just by pure theoretical means, and have that remarkably compare to what you observe in an actual experiment, right? Here's a flow simulation, which is basically what we did, and here is the same idea from an experimental standpoint. You see some flow separations below the cylinder right here, but for the most part, we were able to simulate a real flow field using just some rudimentary concepts in aerodynamics, right? That's powerful. That's pretty cool if you think about it, right? And the first time I did it, I was amazed that we can do this just by just simple math, right? So this idea, this phenomenon of getting lift from rotation of a cylinder is what's called Magnus effect. So for we want to explain Magnus effect, Derek from Veritasium has this really interesting video on which explains the Magnus effect. So in the slide, I will leave a link for Derek's Veritasium's video, so you can go and watch. It's a pretty cool. It explains very well what Magnus effect is and how it's been used on even today for some application like Flettner rotors, and also there's an image of the Flettner rotors on a ship that's used to steer, and there are some RC airplanes as well which kind of employs this Magnus effect. So I encourage you to go and look at it. Right. So coming back to the math, here you have the stream function equations, right? Again, make sure to keep the x naught and y naught in here, because that ideally what I want you guys to do later on is that you can basically combine multiple elementary flows to simulate objects of your own interest, which again, that's what people did back in the day, is that and they did all of these when they had no computers, right? I mean, to even think that, to even see the amount of effort and work they went into developing all these models and having the understanding to visualize how all of this looks in a 2D space, that's pretty cool, right? So right here, again, make sure when you program this equation, make sure that you normalize the radius in the vortex stream function, right? So again, you program this equation, you take this, you take a derivative of this with respect to x and y, you get u and v, and then basically use that to actually plot the velocity vectors, which again will be your your next, it's actually your homework 6 and homework 5, right? Which I will also post along with the series of lectures. Okay, so one other interesting thing that happens in this flow field is that as you keep increasing the circulation of the vortex, you will see that the stagnation points kind of move, come closer and closer, kind of moves down. Some value of circulation you will actually get one stagnation point on the cylinder, and if you increase the circulation even further, the stagnation point sort of lifts from the surface and acts, somewhere over here. So, which is again pretty cool, and you can predict this just by setting VR and V theta as 0. So the reason why we work with polar coordinates is that analytically it allows us to get expression for it pretty, at a much quicker time. So solving for this, you get R equals R, which obviously the radius, the stagnation point will be located on the radius, right? And the theta is controlled by, the stagnation point location along the surface is, controlled by the arc sine minus gamma by 4 pi u infinity R. So again, as you can see, it depends on the free stream and also the circulation, right? So if this value is less than 1, then you have 2 stagnation points. If the value is equal to 1, you have 1 stagnation point. If this value is greater than 1, then you will see that the stagnation point moves away from the surface. So when you program this, in your code, make sure to change the values of this gamma and try to generate flow field that kind of looks like these, and check whether this condition holds. Okay, so again, it's a fun exercise. So again, all of this can only be done if you were able to find the surface streamline and then the surface velocity and pressure, because in the net, in the end, what we really want is we need the capability to create objects, flow over objects using elementary flows, and also be able to predict the lift and drag. Or let's ignore drag for now. Let's just determine, and let's see if we can predict lift. Okay. So in order to do that, you need the surface velocity and surface pressure, right? And in order to do that, you need the stagnation points on the surface in the first place. So again, use the same procedure to get these stagnation points and the surface streamline. Again, think about how you're going to find stagnation points. You find the stagnation points by setting u and v equals 0 and solving for x and y, right? That's how you find the stagnation point. And in order to find the surface or the streamline that goes through the stagnation point, you find that x and y coordinates of the stagnation point, put that into the stream function equation, and you get the value of the stream function that goes through that point, right? And then you basically highlight that. That kind of mimics the surface of the object, right? Which is pretty cool. Then again, we kind of did all that. So once you find the surface streamline, then you basically plug that x and y location, u and v, to actually get the velocity variation around the cylinder. And from there, you can actually get pressures, or you can even plot the CP, coefficient of pressure variation, and get CL, coefficient of lift, right? So I hope, now we were able to simulate flow over cylinder, but think about how you can simulate flow over something that looks like that, with a triangle and an airfoil. So if you were able to place, the elementary flows in such a way that the combination of this will get you a triangle or an airfoil, you can determine the velocity and pressure surround it and calculate the net aerodynamic force, right? Hey, that's pretty cool, right? So hopefully all of this video, makes sense. In the next video, I'm going to talk about the homework that you will be doing, which is related to this elementary flow stream function, Laplace equation, and all that, right? So see you in the next video.